simple stuff you should be able to walk through yourself separately, right? So I should be able to write down in this particular case, remember there are only 3 guys, A, B, C, right? That means there are 8 words, 1, 2, 3, etc., 8 words. For each word, I should be able to write for each of these sentences what their truth value is. Like for example here, what is the truth value of A or C? A is false, C is true, so this is true. Right? So I should be then able to put down the true falsity values for each of them, and I can fill up this table. If I fill up the table, that's how it looks. Right? Up until this is what you've been given. If you fill up this table, this is for A or C, this is for B or not C. This is for knowledge base. Knowledge base means the conjunction of these 2 columns. Right? Knowledge base is the 2 sentences together. So conjunction of the 2 columns. Okay? And then this is the alpha. Alpha is basically, what was the alpha? Alpha is A or B. So now I basically focus on just these 2 columns. I look to see which are the rows where knowledge base is true. The knowledge base is true in these 2 rows and in these 2 rows. Everywhere else it's false. I'm not pulling any rug, right? It's right there in front of you. Then in each of these rows, check whether alpha is true. Is alpha true? We're done. Proved. Attained. That's what attainment is. If you have 10,000 propositions, you write a nice little table with 2 power 10,000 rows. And then keep on asking TS, give me more paper, write all these rows, and then the cows will come home and you'll be dead. You won't be able to do it this way. You need a faster way. Right? But this is one way of doing things. You want to understand how to do things model theoretically. Okay. Okay. Now actually, let me go. This the other one that I want to do. Yeah. So the other way of doing things here is I'm going to make a new column called KB and not alpha. And I want to prove to myself that KB and not alpha is as unsatisfiable as that John came to the party, John didn't come to the party. Remember you thought those are, who would be interested in writing sentences that are unsatisfiable? Well, I am. I am interested in writing KB and not alpha and hoping that it will be unsatisfiable. If it is unsatisfiable, then alpha is a theorem. If it is satisfiable even in 1 row, I'm dead. It's not a theorem. You see what I'm saying? Okay? But clearly you can basically add that, you added that thing KB and not alpha, and thankfully, here is false and false, false, false and false, false, false and false, false and true, false, true and true. KB and not alpha. By the way, this is not alpha, so I should have one more. Whatever is alpha is saying, I should take the negation of it. So KB is false, not alpha is true, false and true, false. False and true, false. False and false, false. True and false, false. True and false, false. False and false, false. True and false, false. True and false, false. If I have 2 power 10,000, I can take a lot more classes. Right? So, this is what is called model theoretic inference. Okay? Here's a question. What if my knowledge base was John came to the party, John didn't come to the party? Do you understand what I'm saying? What if I'm one of these people who are on high drugs? I said, oh, John came to the party, John didn't come to the party. So how many, in that case, knowledge base will be false everywhere? Right? And then false and anything else will still be false. So by this rule, I will say every fact is entailed. Are we in big trouble or what? Did you understand what I'm just saying? if my knowledge base is inconsistent, that means it has no models, then this thing seems to be telling me that any alpha would be true. Any alpha would be a theorem. Is this a problem? How many of you think it's a problem? How many of you know some proofs which show 1 equal to 2 in the end? Do you know any of those proofs? Like, I mean, take this following very simple proof of, I mean, I can tell some many ones, but like there's this one, most of the 1 equal to 2 proofs ultimately start with a premise that is false. From false, everything can be proved. Like, for example, they will try to say 0 by 0 has a value. Well, 0 by 0 has every value. You see what I'm saying? So, in fact, entailment is completely valid if your knowledge base is inconsistent. Now, my question is, do any of you here, we're talking about, those of you who don't believe any inconsistent facts in your head, throw the first stone. Not at me, but somebody else. So the question is, do any of you believe inconsistent things in your head? All of you do. All of you do. Do you say everything is then following from that? So are you using logic? Did you understand what I'm saying? Do you understand what I'm saying? If you ever believe two facts that are mutually inconsistent, and you're still able to somehow live, you're not using logic. Thank goodness. Because logic, the moment there is one inconsistency in the knowledge base, everything is true. This is by design. It's not a bug, it's a feature. Okay? You've been using logic like forever. You never thought about this issue. In fact, this is the same thing. For example, false. So basically, from false you can entail anything, and that's exactly is what this thing is saying. And here is another way of looking at too. Like in that case, all the rows in which knowledge base is true would be empty rows. There are no rows where knowledge base is true. My only question is alpha true in every row where knowledge base is true? Yeah. Yes or no? Yes. So alpha is entailed. Can you give me a world where knowledge base is true, alpha is false? No, you can't, in which case alpha is entailed. This is one of these things that people have to understand about logical inference, that you always take it for granted. From false follows everything. Okay, before we go into the resolution, the proof theoretic part, which is going to be the extended session, let me mention something which actually is connected to an entire chapter that we skipped called constraint satisfaction. If you have, basically what I did in this last column here is I was trying to solve a problem saying, here is a logical sentence, can you prove it is unsatisfiable? So it's what's called the Boolean unsatisfiability problem. How many of you have heard of Boolean satisfiability problem? Boolean satisfiability problem essentially is, given a propositional logic formula, is there a single world at least where that formula evaluates to? And if so, give me that world. Do you understand what I'm saying? Really, nobody heard of Boolean satisfiability? How did you get to senior level, graduate level? So did you guys hear of things like NP completeness? Yes. How did NP completeness come? What was the original NP complete problem? What is the original NP-complete problem? What is the problem that somebody first had to show? Remember the way whole NP-completeness theorem works is for any random problem, you will say this God-forsaken problem can be reduced to that. So that if you can solve that in polynomial time, you can solve this problem in polynomial time too, and nobody believes this problem can be solved in polynomial time. What is that problem? Boolean satisfiability. Stephen Cook got Turing Award for showing that Boolean satisfiability problem cannot have polynomial time solution unless p equal to n. That's the original NP-complete. I bit this up at a huge climax and it fell flat because nobody heard of Boolean satisfiability. It's very important to know Boolean satisfiability. I mean, propositional logic permeates computer science. This calculus stuff you are supposed to have forgotten long back and you have been made to remember again. But the rest of the stuff, like the discrete math that you did, is basically Boolean logic is well connected to discrete math. All your algorithms and the complexity theory are connected to Boolean logic. Boolean satisfiability problem essentially is this problem. Given a bunch of clauses, a clause, this one says, this basically PSU is PRSRU. Okay? And then not P dash Q, comma Q is not P or Q. And so on. Given a bunch of these clauses, can you tell me truth falsity values of P, S, Q, R, etc., such that all sentences are satisfied? Every clause can be thought of as a constraint. And you're trying to find a model where all constraints are satisfied. This is Boolean constraint satisfied problem. Okay? So model checking that we looked at really, and I'll take 3 more minutes and then I'll stop for the normal session and the next session will start. But I just want you to understand that to solve problems like that, and here's a much simpler version of that problem. Here is a party problem. Constraint is, for constraint 1 is either Joe didn't come or Tom didn't come to the party. Constraint 2 is either Tom came or Mo didn't come to the party. Constraint 3 is Joe didn't come or Mo came to the party. My question is there a party that I can throw where all these 3 constraints are satisfied? In fact, I can think of this as I have friends who don't get along, and I'm trying to throw a party. Okay? And if, basically either I should not call Joe or I should not call Tom, because both of them are there, I'll have reasons. So these are my constraints on my party planning. My question is there a configuration of parties that I can throw where I can tell I will send the invites and only those people will come, and then I will know whether or not, and then that will be a successful party because all constraints are satisfied. The question then is, how do you solve this? One idea, of course, to do this is draw a table like this. Now, it turns out that constraint satisfaction problems of this type are extremely useful. For example, they can be used in timetabling. They can be used in scheduling of jobs. They can be, versions of these essentially are used in your airline scheduling problems. Okay, times of the way airlines schedule their crew, their flights, etc. Logistics, and of all the important things, Sudoku. They all essentially can be written as a Boolean satisfiability problem. The dumb way of doing it is writing a huge big table. The simpler way of doing it is, here is a search technique that I'll give you. Start with some guy, Joe. Okay? And either Joe is coming to the party or not coming to the party. If Joe is coming to the party, then I will consider some other guy, Tom. Is Tom is coming to the party or not coming to the party? And so if I expand this tree, then the leaf nodes will be party configurations. The only question is, if any of the constraints is violated at any place during this tree search, I can stop that whole branch. Do you understand what I'm saying? Because once a constraint is violated, it's not going to improve. So this is a beautiful search technique. I just essentially considered variables as the search nodes, and I considered their values in the different branches, and anytime the current partial party is already sunk because it's violating one of the constraints, I won't expand it any further. So I told you Boolean satisfiability, I said it's a great problem, and I said it's actually search. If I'm doing this search, 2 questions before you go off. What search would you use? Breadth first or depth first? How many people think they want to use breadth first for this? How many people want to use depth first for this? You better use depth first. All parties are created equal. All successful parties are created equal. You just want to find one successful party. Right? Depth first. You forgot that whole thing. I'm telling you that you should use depth first. Now, the second question, and then we will really go into the extended session. Would you use iterative deepening depth first or just normal depth first? How stupid should you feel if you use iterative deepening depth first? What? No. Why would you not do iterative deepening depth first? Yes, go ahead.
Because you'd lose all the progress you just got on.
No. Yes.
All the goals is at the bottom.
All successful parties are at the 3rd level. Not all parties at the 3rd level are successful. But all successful parties are at the 3rd level. If I ever were to give you a search tree and say that all goals appear in the level 15, and you want to do iterative deepening depth first search, who are you trying to impress? Constraint satisfaction problems are solved by depth first search directly. We'll stop here, we'll let other people who want to go, and then I'll continue with Okay. So we sort of took a digression. We were trying to kind of do theorem proving. We wanted to prove knowing what we know is a sentence entailed. And we actually found that checking entailment involves, as one way of checking entailment, is actually proving unsatisfiability, Boolean unsatisfiability. So in fact, in logics, in propositional logic on words, there are really 2 kinds of problems. Let me skip over all of these. Okay. There are 2 kinds of problems: entailment, satisfiability. Those are the 2 most important problems in any logic. One is, given a bunch of logical constraints, is there a model that satisfies all the constraints? The other is, given you have a bunch of constraints, can you write this as a constraint that will always hold whenever these other constraints are there? Do people understand what I just said? This is the yin and yang of logic. Satisfiability, theorem proving. So in fact, satisfiability and entailment are model checking is basically satisfiability, and theorem proving is entailment. Okay? Remember I said Boolean satisfiability is NP complete? So you know that propositional model checking is NP complete problem. So what is propositional theorem proving's complexity? It's the conjugate problem. So it's co-NP complete. As far as you are concerned, hard problem. Okay. So in computer science, we talk about complexity in terms of NP hard and in NP completeness and higher up. Boolean satisfiability is an NP complete problem. Okay? And it turns out that, it turns out that entailment is nothing but Boolean unsatisfiability. Because given an entailment problem, there is an equivalent Boolean unsatisfiability problem. Yes or no? Because that's exactly what I did. I don't want to go back to 2 minutes, but that's exactly what we did when we threw this KB and not alpha slide, not alpha column, and said it's alphas. So model checking and theorem proving are yin and yang. In fact, they are connected. So the good solutions for model checking, Boolean satisfiability, would be much better than just the one that I showed you, which is already very good because as soon as in that search tree you get a partial assignment that is dead, you can stop searching. That's a huge win. But there are other things that you can do which involve, as part of doing model checking, you do a little bit of theorem proving. And those are from constraint satisfaction literature, those are called constraint propagation techniques. And if you do that, it will cut down the search. So model checking can help theorem proving can help model checking. And they are yin and yang. Useful to remember. Okay, there is a whole bunch of stuff here that you can look at, but that's important too. But now, what we want to do is the syntax of the inference rules quickly. Get you to a point where at least we sort of realize that this propositional resolution theorem proving is the greatest thing. In the sense, one rule you can solve. One rule basically is both sound and complete. Okay? So here are some rules that are sound but incomplete. Okay? So for example, the modus ponens rule. Okay, if the things on green are in the knowledge base, and the thing in blue is being written as entailed. Okay, so if A implies B and A implies B is true and A is true, then B is true. Okay, then so you can write B as entailed basically. Then similarly, modus tollens, if A implies B is true and not B is true, then you get to write not A. Similarly, modus Pythonus, this is actually not a rule. Modus Pythonus says A implies B is true, A is not true. Can you say B is not true? Do you see what I am saying? A implies B. Just because A is not true doesn't mean B won't be true. Because somebody else could have been, B may be connected to both A and W, for example. And W is true, so B is again true. Do you see what I am saying? Remember when we say a knowledge base entails alpha, you are only saying that these are all the places where alpha is true. You just are happy enough if in the few words where knowledge base is true, alpha is true also. Do you see what I'm saying? So it could be true in some other places too. And that's the reason why not A implies, so A implies B, and not A does not give you not B. By the way, how do you prove this? How do you prove that this is sound or not sound? Okay, it turns out, let's say that modus tollens, which is a nice little thing, and this is, by the way, if I must tell you, this is a homework problem, this is the exam problem, this is the kind of stuff that people check to see whether you understood these concepts. Okay, so for example, how do I prove modus tollens is sound? I basically write down the truth table. A implies B, the knowledge base will have be A, B, and not B. And then I will write not A, and then I will check if in fact in all the rows where knowledge base is true, not A is true. This is the first principles proof. You can also, it turns out that if you have already proved some other rules to be sound, you can use them to prove this rule to be sound. That's also possible. In fact, we'll do that a little later. Yes, go ahead.
Does this actually check soundness?
This is soundness, yeah.
It checks soundness.
It's soundness. If you can do this, it's sound. Completeness, on the other hand, has to be done by mathematical induction. Or you can disprove completeness by giving an example, a counterexample, where I know this is entailed and you are unable to prove it. You see what I'm saying? Okay? So how do I, for example, show that modus ponens is definitely not complete? I can write the following thing. Either Tom came to the party or Tom did not come to the party. There's nothing wrong in writing that, by the way. Tom came to the party and Tom did not came to the party, that's bad. In fact, anything can be written. They're all syntactically correct and one which is unsatisfiable. Tom either came to the party or didn't come to the party. It's actually a tautology. For those of you who remember, it's true in every word. Okay? And if Tom came, John is happy. If Tom didn't come, John is happy. John is happy kind of a guy. My question is, do you know John is happy? Who said no? You seem to be an unhappy guy. You don't want to make John happy. Just look at this. You reason it out. The world can only be either Tom came or Tom didn't come. If Tom came, John is happy. If Tom didn't come, John is still happy. So John is happy in every world. So John is happy. Right? Can you prove this using modus ponens? Only modus ponens? No. It's not possible. This is the counterexample showing modus ponens is incomplete. In fact, this is a great counterexample to remember. This requires here, what we wound up doing, this requires case analysis. Right? It requires case analysis. You have to consider the case where Tom came and the case where Tom didn't come. In fact, this is not, doesn't have to be actually, this doesn't have to be a tautology. Here is another version. Either either Mary came to the party or some other name, Rao came to the party. Okay? And if Mary comes to the party, John is happy. If Rao comes to the party, John is happy. Is John happy? Again, yes, happy. Case analysis. Either Mary came to the party or John came to the party. Either which way, John is happy, so John is happy. Modus ponens cannot do this. You agree that, first of all, you agree that this, from your reasoning, you see that John is happy. To actually prove that it's entailed, you can do your truth table. Okay? And show that in every row where the conjunction of these three things is true, John happy is true. In fact, take this as an exercise to make sure that you understood. Prove either this or this, one of them, by truth table method. That means it's actually entailed. And yet, modus ponens is not allowing you to show that it's entailed. You see what I'm saying? That's why modus ponens is incomplete. Similarly, there are things like chaining rules. If A implies B, B implies C, then A implies C. That's a new rule. That actually is also true. That's also a sound rule, but it's still not complete. Okay? So it turns out that if you just use modus ponens, you can prove some theorems, but not all theorems. How many of you have heard prologue? Prolog basically, without the cut operator, those of you who know Prolog know what I'm talking about, is essentially a modus ponens solver. Modus ponens is actually a lot more intuitive. Case analysis is hard for us. This one is easy. But if the world is divided into 10,000 cases, to check that something is holding, I need to check that in all those cases that thing is holding. Quite a painful thing for people to do. Normally, those are the places where logical paradoxes come. So modus ponens, it turns out, actually, if you just do modus ponens and to prove a theorem, then it will only be taking polynomial time. It won't take exponential time. Even though full theorem proving is NP hard, just the part where you can only use modus ponens and prove, that is only polynomial. Do you see what I'm saying? Okay. Again, in terms of just complete but unsound, as I said, S-MOM logic, where you say for everything you say yes, it's entailed. In which case you would also have said, for all the things that are truly entailed, you would have said they're entailed. Because of which you are vacuously complete. But you're not sound. Because there are things that you will say are entailed, they're not actually entailed. That lets us to come to the part of the, so actually this one is basically showing why, this other part is showing why modus Pythonus is an unsound, inference. Just as I showed one is in sound inference, I showed the other one is unsound. Basically, I'll be able to show that there are two places where knowledge base is true. In only one of the places, the fact is true, the other is false. So you couldn't have written the fact to be entailed. So ultimately, you show soundness by the truth table method. Truth table method is the semantics. Okay? So how about sound and complete? This is basically this is a variation of that Rao-Barkley problem. W implies J, not W implies J. Is J true? Well, modus ponens can't derive it, but you know it is true. Because it's entailed. Okay? Okay. So that brings us to this last rule called the resolution rule. Okay? Cute rule. All it is basically saying is if you happen to have statements of the following form, alpha or beta and not beta or gamma, where alpha, beta, gamma are all propositions. That means you are only allowing sentences in this form, where each of the sentences in your knowledge base have to be what are called disjunctive clauses. A clause